Hi Lala, welcome back to your videos. I think this is your video number 5 right now, where we've covered up all the previous stuff related to lines, and now we're finally going to move to rate of change and what actually your derivation is. So for example, he's giving you this function. He says consider this function y is equal to x squared plus 2. The first thing you notice about this function is that it is not a linear function, it is a quadratic function. So every time you have a quadratic function, or you have a non-linear function, essentially speaking, you should know that the gradient of the line is not the same throughout the entire curve, because the curvature of the line changes. So from this point to this point, the gradient is different. In fact, not only from this point to this point, but the gradient at this point is different from the gradient at this point, is different from the gradient at this point, is different from the gradient at this point, is different at the gradient at this point, because this line is not straight. Had this line been like this, the gradient would have been the same all over. Or had this line been like this, which is, I'm trying to show you a straight line, the gradient would have been same all over. Or if the line would have been like this, the gradient would have been same all over. So you get my point. Basically, every time you have a straight line, which is that x is to the power 1, the gradient throughout the entire line is the same. However, the basis of differentiation and the basis of calculus is built on this fact that when you are given a line which does not have a straight slope, the gradient changes across the line. And that usually happens, or it actually always happens, for a line where x is a power greater than 1. So here he's trying to say to you what I've said to you already. The gradient is different at each value of x. We can currently find the gradient for a specific value of x. So for example, at x is equal to 1, we can find the gradient there. Or at x is equal to 3, we can find the gradient of the line there. Now he's going to go on to tell you how to find the gradient of the line, let's say at x is equal to 1. And the way to go about this is, he says, to find an approximation for the gradient at point xp is equal to 1. Sorry, I'm closing my windows in case you could hear noise outside, because I could. Anyhow, so for example, if he says that find the gradient of the point at xp is equal to 1, we consider a point larger than 1 to its right, for example, where xq is equal to 3. So basically what he's done is that he has, for finding out the gradient of x at this point 1, he finds a point which is slightly larger than 1, which is x is equal to 3. So he's taken out these 2 points, 1 and 3. This he is labeled as xp. Let's just label this point as p and this point as q. I don't know what is wrong with the software. So this would be, so this point is xp and this point is xq. So to find the gradient at the point xp, he says find a value which is slightly larger than xp, which is xq, and then at that point you go see what is yp, what's the y when your x is at this value, and what is your y again, your yq when your value of x is this. Again, it's the same way. You're using the same formula, which is m is equal to change in y over change in x to find your gradient. But in this case, the only difference is that the gradient is not going to be constant throughout, and we'll get to that later, but let's find out the gradient. So he says, so for example, to find approximation for the gradient at point xp, we consider a point larger than 1 to its right, for example, xq. So at x is equal to 1, now this is the same equation he's taken. He's just putting substituting the values of x in that equation. If you remember, the equation was y is equal to x squared plus 2. So take a look at this equation right now. Where's the equation? Yeah. Y is equal to x squared plus 2. That's the equation. So what you're going to do is you're simply going to substitute the values of x into that equation. So at x is equal to 1, this would become 1 squared plus 2. And then y would become is equal to 3. At x is equal to 3, you substitute the value of 3 into this equation. This will become 3 squared plus 2, which is 9 plus 2, 9, 10, 11. Y would become is equal to 11. And you can see these values of corresponding values of y from the graph as well. So it's pretty much the same thing. So for those values of x at x is equal to 1 and a slightly higher value of y at y is equal to 3, he puts these values into the equation x squared plus 2, and he gets the corresponding values of y, which is y is equal to 3 and y is equal to 11. And then he applies the same formula that we've done before. y1 minus y2 over x1, which is your value that you took for x before substitution, minus x2, and this is the same rate of change. There's nothing different here. This is the gradient formula, y1 over y2 minus x1 over x2, and he gets 4. But he says this rate of change, this gradient, is with a caution that only at x is equal to 1 is an approximation, right? So this he says is gradient is equal to 4 is only at this point where x is equal to 1. It's not for the entire curve, because as the curvature changes, the gradient changes as well. So it's only at this point where x is equal to 1. Then he tries to test your knowledge and he says, how about when xp is equal to 1, what would yp be? And at xq is equal to 2, what would yq be? Again, the same way you're going to apply the formula. You'll substitute the value of 1 into this equation. This is 1 square plus 2, so you'll get 3 over here. Yp would be 3. And for xu is equal to 2, you're going to get your yq, which is you substitute over here, which is 2 square plus 2, which is 4. Then you'll find your rate of change, which is 3 by 4. 4 plus 2, 6, 3 by 6, which is, it is actually 3 by 6, yeah, which is 1 by 2. So your rate of change at point 1 is going to be different when you take the point xq, and your rate of change at point 1 is going to be different when you take xq is equal to 3. So over here, your rate of change will be 4. Over here, when you'll calculate, I think it will be 1 by 2, because that is what 3 by 6 is. Anyhow, do the math, but you'll find your rate of change to be different over here. The reason for this exercise was to show to you that the rate of change is not constant, and this method only gives an approximation for the gradient along the dashed line PQ and not along the whole curve. He's saying that this is just going to give an approximation of the rate of change along this line PQ, and it is not the rate of change or the gradient of the whole line. It's at best it's an approximation. Hence, it is better for the points P and Q to be as close as possible to each other as to get a reasonable answer. So he's saying the closer that your points XP and XQ are, for example, if x is equal to 1, then y must be, so when x is equal to 1, then you should get a point which is extremely close to x, like for example 1.5 or 2, to get a better approximation of your answer. Then he goes on to say, when we draw the curve of a function, we see the rate of change is directly related to the steepness of the curve. So the rate of change is often related to the gradient of slope. This is not very important. He's just saying that the steepness of the curve is the same thing as the gradient. Now he's going to take you to the algebraic approach. But before we go on to the algebraic approach, let me see how much time is left and if we need to pause and go to another video. Okay, we do. So I'm going to discuss the algebraic video in the approach in the other video.